Hello everyone, I am Ard, a student at ETH Zurich, and I will present a joint work with Martin and Chen-Da on multi-threshold asynchronous reliable broadcast and consensus. Broadcast and consensus are two of the most fundamental primitives in distributed computing and have been studied extensively. These protocols, however, take a different form depending on the underlying model. Here, we consider the case where the network is assumed to be complete, meaning that all parties have a direct channel to every other party. Asynchronous, meaning that the messages in the channels can be delayed arbitrarily. However, each message in the channel is eventually received. And public, meaning the adversary can read all the communication between the parties. Next, the adversary is assumed to be a central entity who can corrupt some of the parties. The number of the parties is denoted by F, is assumed to be Byzantine, meaning that he can make the parties behave in any arbitrary manner. And finally, has unlimited computational power. That is, we argue about security in information theoretic sense. So, why study multi-threshold protocols at all? In classical protocols, the security guarantees are typically provided in all or nothing fashion. If up to T parties are corrupted, all security guarantees remain. However, if more than the T parties are corrupted, the protocols do not provide any security guarantees. On the other hand, multi-threshold protocols are a generalization which provide different security guarantees depending on the amount of corruption, thereby allowing a graceful degradation of security. We consider both reliable broadcast and consensus protocols, and we consider separate thresholds for each of the property guarantees, namely validity, consistency, and termination that each primitive provide. Our work shows a very complete characterization for both primitives on what is achievable and what is impossible. We start with broadcast. Broadcast allows a specific party, which we call the sender, which we denote also by S, to distribute a message among n recipients in such a way that all honest parties obtain the same message, even when some of the parties are dishonest. Typically, broadcast is defined in property-based manner. In this talk, however, we consider the generalization of this definition. As mentioned before, we consider now for each property a different threshold. More precisely, if the number of corruption is bounded by some threshold TV, then we want the protocol to achieve validity. What validity basically says that if the sender is honest, then all honest recipients output the sender's value M. Next, we have consistency. Here also we have a separate threshold, namely TC. And as long as the number of corruption is below this threshold, the protocol must achieve consistency, which basically says that no matter what the sender does, even if he is dishonest, the recipients output consistently. It doesn't matter which message, as long as it's the same message M prime. Finally, we have termination, which basically says that the parties eventually terminate. Note that in broadcast, termination cannot be guaranteed similar to other protocols, but we only rely on partial termination. This comes from the fact that if the sender is dishonest in the beginning of the protocol and he doesn't send anything, the recipients can never distinguish whether this was because of the delayed messages or really the sender didn't send those messages. So basically the recipients can never terminate. So what we require then is that if the sender is honest, then every party eventually terminates with some value. But if the sender is dishonest, then either no one terminates or everyone terminates. Next, we go to the second primitive, namely consensus. In consensus, the goal is to reach agreement on a common value, where each party has an input. Similar to broadcast, we consider multi-threshold consensus. So if the number of corruptions is below some threshold TV, then we want the protocol to achieve validity, which basically says that if the parties start with the same input, they keep this value. Second, we have consistency. Here again, a separate threshold TC. And in context of consensus, consistency means that if the parties start with some input Xi, the ones that output consistently some value Y. And finally, we have termination. Here again, a separate threshold, which we denote with TT, and which basically says that if the parties start with some input Xi, eventually they terminate with some output epsilon I. Here we differentiate between two types of termination. One is with probability 1, which is also known almost surely, and the other with probability 1 minus epsilon, where epsilon is bigger, strictly bigger than 0. Next, we go to our results. The first result of this paper is multi-threshold broadcast is achievable if and only if maximum of TC and TV plus 2TT is smaller than n. The second result is related to almost surely consensus, where we show that we can build an almost surely consensus if maximum of TC and TV plus 2TT is smaller than n, the same bound as in broadcast. In addition, 2TV plus TT is smaller than n, and TT is smaller than n third. The first two bounds are known to be optimal. However, whether TT is smaller than n third is necessary is left as an open question. However, we show that if we relax the termination property, namely if we require the parties to terminate only with probability 1 minus epsilon, then we don't need this bound, and we show that multi-threshold 1 minus epsilon consensus is achievable if and only if maximum of TC and TV plus 2T is smaller than n, and 2TV plus TT is smaller than n. In addition to that, we also saw that if we assume a global coin, then actually we can also achieve multi-threshold almost surely consensus if and only if maximum of TC and TV plus 2TT is smaller than n, and the bound 2TV plus TT is smaller than n. We start with broadcast. First, I will present you the broadcast protocol proposed by Braha, which is optimal as long as T is smaller than n third. So this is the case only for a single threshold. Now, with a little bit of thinking, this protocol can be generalized for our setting as follows. So instead of n minus t in line 2, we now wait for n minus tt messages, because to guarantee termination, we cannot afford to wait more than n minus tt, because since tt can be corrupted, they might never send those values. Line 3, t plus 1 will be replaced with maximum of tc and tv plus 1. And in line 4, similar to line 2, we replace it with n minus tt. However, if we think about this, this protocol works only as long as the bound of termination is below the maximum of tc and tv. And the reason for this is that if we analyze this protocol, then the termination property depends on the consistency property. So why is this? In line 4, some party that received n minus tt ready messages, he can safely terminate and output m prime, because he knows that from those messages, at least n minus 2 tt parties, which is in our case at least maximum of tc and tv plus 1, will receive these values, and they will also send ready messages. So basically, the first honest party that received n minus tt, then we know that in the network, maximum of tc and tv plus 1 ready messages are there. And those will be received by all honest parties, which in return will make those parties to send ready messages as well. And this means that at some point, all the honest parties will send ready messages, so they will all reach line 4 and terminate. But if the ready messages are not unique, so if the protocol doesn't guarantee consistency, then obviously this argument doesn't work anymore. And therefore, the protocol breaks. But in order to make sure that also we guarantee termination, even if the parties don't agree on a value, but they simply want to terminate, then we can do this as follows. Now, in line 4, when someone receives n minus tt values, they will also send the terminate flag. And the other parties will count this terminate flag as ready messages, kind of as a ready star, where it counts for all the types of ready messages. And in this way, the parties that terminate will let all the other parties that he actually terminated. So it doesn't matter with which value he terminated. However, of course, as long as the number of corruptions is below maximum of TC and TV, we still want to achieve consistency and validity. And that's why we require that at least in the network to be maximum of TC and TV plus 1 parties. And these are guaranteed to exist because the first party will receive from honest parties at least of only ready messages. So as long as no one terminated so far, no honest party will send the terminate. So this will guarantee that in the network there are these many ready messages, and therefore these either will be amplified or will be counted as terminate to other parties. So with this trick, kind of, we guarantee also termination as long as the number of corruption is below TT, but also if the number of corruption is below TC and TV, we guarantee consistency and validity. For the other direction of the proof, basically the optimality of the algorithm, we divide the bounds into two different bounds. First, we show that TC plus 2TT needs to be smaller than N, and then we show TV plus 2TT needs to be smaller than N. So let's assume by contradiction that there exists a protocol with TC plus 2TT greater or equal to N. Then we divide the participants, the recipients, into three groups, A and B of size TT and C of size TC. Here we have the sender who is broadcasting a 0. This notation here means that all the messages between A and B are simply delayed. Now, because of the termination property, the parties in A cannot tell whether B is corrupted or the messages are delayed. So even before any messages here are scheduled, the parties in A will terminate. The same with B. So what this means is before any messages in between A and B are scheduled, all the parties here will terminate. But here, all the parties are honest. We simply only delay the messages between A and B. So since they are honest, they will output the sender's value, namely 0. The same argument holds here. So eventually, all parties will terminate and output the 1. Now consider the adversary who has corrupted TC parties emulate this protocol. So towards A, he emulates as the sender is broadcasting a 0, and towards B, he emulates as the sender is broadcasting a 1. Since it's the same setup, then A would output a 0, B would output a 1, which is in direct contradiction to consistency. Similar to this one, we can build also for the other bound a scenario based. One can argue that here all parties would output a 0. In particular, first A and C needs to output a 0, but because we have this partial termination, since A and C output a 0, then if someone terminates, everyone needs to terminate. So B also will terminate. Similarly here, everyone here would output a 1. But what happens if the corrupted parties, which is of size TV, emulates this protocol? Then since it's the same setup, A would output a 0, B would output a 1, which is in direct contradiction to validity. Great. We have seen a multi-threshold broadcast protocol, which is optimal. But before we go to the protocol of consensus, there is an important mechanism that is used in our paper, which was proposed by Braha back in 1987. The technique is called correctness enforcement, and what it basically does, it forces the corrupted parties to behave honestly, or they are simply ignored. The idea is that if we have round-based asynchronous protocol, as in here, then even if we use reliable broadcast in line 1, the protocol guarantees that the Byzantine parties send the same message to all the parties. However, we cannot control the content of the message. For all we know, he can broadcast a message that was not supposed to be broadcast at all. However, if we have a round-based protocol as this one, then we can do more. As we can see here, protocol with this structure follow this pattern. First, everyone has an input xi at around k. They broadcast this input, then everyone waits until they receive a set of those messages. Typically in asynchronous protocol, this is of size n minus t, and then they update the value for the next round based on these messages. Now, what correctness enforcement does is, besides receiving the messages during the broadcast protocol, it requires also the messages to be validated. What this means is, if someone sends you an input, you first wait whether there are possible inputs of previous round that could have made this party to actually update is input to this particular value. If this is true, only then the message is validated. In other words, message is validated only if it could have been sent by an honest party. We now go to the multi-threshold consensus protocol for the almost surely terminating case. So similar to broadcast, first we show the Braha's consensus for a single threshold T, and then we try to generalize it for the multi-threshold setting. The main idea of consensus is to use randomness and by chance to reach an agreement. Due to the FLP impossibility result, non-terminating executions of any consensus protocol are inevitable. So first we have a majority round, and then the parties, if there are enough values where they agree, they propose this value, and then in the end, if there are enough proposals, then they decide, or if there are more than T+1, then they keep this value, or finally they throw a coin. So this protocol works for a single threshold as shown by Braha, and in order to generalize this, we do similar. First, we replace the n minus t with n minus tt, and T+1 is actually replaced here with TT+1. And of course, now the broadcast protocol needs to be substituted with our multi-threshold broadcast, where the parameters that we choose here is TS and TT, where TS is defined to be n minus 2 TT minus 1. Note that this is achievable because, as we have shown previously, this kind of TS would be similar to maximum of TC and TV in the context of broadcast. Now one can show that this protocol works, however, as long as TT is below 1/3. And the main idea is as if the termination bound is below 1/3, then we can allow to have consistency and validity above 1/3, in particular above the termination. So in other words, up to TT, now we kind of have all the properties as in the single threshold, but between TT and consistency and validity, we only give up termination. So, and why would this work here in our case? Well, the idea is very simple. So up to TT, the same analysis as for the single threshold applies here as well. But if we kind of have more corruptions than TT, the only thing that can go wrong is the broadcast protocols to not terminate. But this only makes some parties to get stuck in some rounds, but still consistency and validity are fulfilled. So as long as any party makes progress, the multi-threshold broadcast and kind of the correctness enforcement scheme make sure that they progress in a correct way. So what happens if the number of corruptions is above 1/3? First, the correctness enforcement simply fails. We know that maximum of TC and TV plus 2TT needs to be smaller than n. And if TT is above 1/3, then necessarily maximum of TC and TV is below 1/3, and therefore also smaller than TT. This means that there is a region of corruptions between maximum of TC and TV and TT, where reliable broadcast now does not guarantee consistent validity, but only guarantees termination. But this is not good enough correctness enforcement, because there we require the messages to be validated in order to proceed into the next round. And if there is no consistency, then those messages can be validated anymore, and therefore parties will get stuck and never terminate. The second problem is with respect to coin. There we had the technique in Braha where if enough honest parties were lucky, then in the next round there was a majority decision which made sure that everyone will update to the same value and everyone will terminate in the next round. But this technique doesn't work if the number of corruptions is above 1/3, because now there is always a way for the corrupt parties to choose the coins in such a way and schedule the message in such a way such that in the next round there are inconsistent majority decision, and therefore parties will never terminate. Finally, even if we assume a common coin, there is a very subtle problem with Benor style protocols, which was shown by Aguilera Tog in 2012, that even if we assume a global coin, the actual Benor protocol actually doesn't terminate. And the idea is very subtle and requires reasoning between different rounds and phases. So it's very counterintuitive. If we use local coins, Benor terminates, as we know. But if we actually plug in the global coin, then it doesn't terminate anymore. So how do we solve these problems? The first one is related to correctness enforcement. And the main idea is to use a different version, which we call detectable correctness enforcement. What we basically do here, we plug a different primitive, not a multi-threshold broadcast that we saw in the beginning, but a slightly different version, detectable broadcast. So the properties that we want here is kind of, if the number of corruption is below maximum of TC and TV, then we have the same thing, so misbehavior is prevented. But if the number of corruption is below TT, then what we require is that misbehavior is at least detected. But this is at the expense of the termination properties, so the parties are not required to terminate anymore. The next is the common coin. So the main problem here was that the corrupted parties might choose the coins in a malicious way. But let's assume for the moment that the only honest parties are allowed to throw a coin, then we are practically done where we can do this protocol. All the honest parties in the R choose a 0 or 1, and they broadcast this value, and then every honest party will update this value to the first broadcast that they output. However, of course, this R is not necessarily made of only of honest parties, but what we do is we cycle through all the subsets, and we have guaranteed that at least one of those subsets will be only made of honest parties. So in that particular phase, if the parties are honest and lucky, then we kind of achieve a common coin. The last one was related to this subtlety related to Benor and relation between rounds. And what we do here in order to kind of analyze the rounds independent of each other, we add an additional round in the beginning of each phase, which we call a locking round. And this makes sure that when the parties run a common coin, so the first honest party, when he throws a coin, no matter whether it's a 0 or 1, in this particular phase, it's already locked whether deterministically the parties will choose a 0 or a 1. So there are no relation between different phases, and this simplifies the analysis and makes possible to use a global coin even in these Benor style protocols. Finally, we additionally have in the beginning a majority round. This is because of the validity requirement. So if all honest parties start with 0, then they do a majority round, which makes sure that everyone will update to 0, and then this way everyone will decide for 0. And now the termination is a bit more tricky because for detectable correctness enforcement, we gave up kind of the termination requirement. So in order now to do this, the idea is to build a termination protocol on top of this underlying protocol. And there are two changes that we need to do. First, we fix the number of phases in this consensus. So now we don't have any more almost surely terminating consensus, but only with probability 1 minus epsilon. And the intuition for this is that in order detectable correctness enforcement to work, then need to be only finite many messages. If there are infinitely many, then some messages might actually never be scheduled because there are always other messages that can be scheduled. So this requires them to fix the number of phases. And again, if some parties then kind of decide in these locking rounds and by chance some parties reach an agreement, then they kind of send the ready messages. And then with the same technique as in broadcast that we used, we kind of make sure that these ready messages will be amplified. And with terminate flag, we make sure that all parties will terminate eventually. So on top of that, basically, we have a very similar protocol as in the broadcast that we presented at the beginning. And this makes sure that then eventually every party will terminate. Great. Now we have shown how to build a multi-threshold consensus where the parties are required to terminate with probability 1 minus epsilon. For the optimality of this protocol, the impossibility proofs are very similar to the one that I explained for broadcast. They are all scenario-based. Therefore, we won't go into details for this part. But interestingly, now by combining these ideas, we also can show that we can build almost surely terminating consensus even for TT above and third. However, for that we need to assume a global coin. Whether this is necessary or really for almost surely terminating consensus without assumption of global coin, TT smaller than in third is required, is left as an open question. Thank you very much for listening.